Well, hi everyone. In this video, I'd like to talk about how we can use the inclusion-exclusion principle together with the subtraction trick in solving counting problems. Generally, the inclusion-exclusion principle is used when we want to count up a union of a variety of scenarios that may in fact have overlapping arrangements that we are counting. In such cases, we have to account for that overlap by using the inclusion-exclusion principle. But let's also remember that one of the other very well-known counting strategies is the idea of subtracting violations. In other words, subtracting from some large total count those arrangements that don't satisfy whatever constraints we might have imposed. Well, but what if those violations occur with several types that themselves have overlap? In other words, what if the part that we're subtracting actually requires the inclusion-exclusion principle? The violations, what if these violations actually overlap with one another? So I'm going to show you an example that will illustrate exactly that situation. And I'm going to read this example out loud, especially because I don't want you to be confused by the glare that is maybe hiding some of the words here. I'll read this aloud with you, and then we'll talk about how to use the inclusion-exclusion principle together with the subtraction trick. In how many ways can we buy 18 pieces of fruit? And I'm going to look at apples, oranges, bananas, and pears. And the constraint is that we want to buy at most 9 apples, at most 6 oranges, and at most 5 bananas. Now, I'll point out here this word "and." We generally think of using the inclusion-exclusion principle when there is an "or" that dictates a variety of scenarios that we would like to count up in some kind of a union. But when we're doing a negation of a bunch of scenarios like this, at most 9 apples, at most 6 oranges, and at most 5 bananas, we're going to be subtracting something that's viewed as an "and." And when you negate an "and," the De Morgan's laws of set theory turn that "and" into an "or," as it turns out. So we actually are going to use the inclusion-exclusion principle here, even though this is a statement with the word "and" in it. So in order to solve a problem like this, what we often would do is solve the problem without any constraints at all first, and then go back and subtract violations. So let's see if we can do that. To start off our solution, what we can do is we can try to solve this problem without constraints. And I need some notation to help me set this up. So I'm going to let x1 be the number of apples that are purchased. Okay, and then I'm going to let x2 be the number of oranges that are purchased. And then x3 will be the number of bananas. And x4 will be the number of pears. Now, if we assume that these pears are all identical to one another, and these bananas and oranges and apples are all identical to one another, then we certainly are allowed repetition here. And at the same time, it doesn't matter what order we purchase these 18 pieces of fruit in. So order does not matter, and repetition is allowed. This is a buying fruit scenario that we can use stars and bars to solve. But in particular, I'm looking for solutions to the following equation. x1 plus x2 plus x3 plus x4 equals 18. And when I say I'm looking for solutions, I'm looking for integer solutions, specifically non-negative integer solutions. We cannot purchase a negative number of fruits or a fractional number of fruits here. So we're looking for integer solutions that are all at least 0. So if we wanted to find the number of solutions to this equation without constraints, let's just point that out here, that if we do this without constraints, we can view this as 18 stars together with 3 bars. The bars sort of create 4 bins, right? 3 bars will create 4 bins for the 4 different types of fruit that we have. And then we just simply need to choose 3 bars, 3 places to put those bars, essentially. So this becomes stars plus bars, choose bars. In this example, that would be 21, choose 3. This is without any constraints at all. But now I want to address the potential constraints here. And I'm going to form those constraints as violations that can take on actually 3 different types, right? So what we could do here is we could create sets to represent arrangements that violate the constraints. For example, the set A could be the set of valid solutions from this 21, choose 3, but with x1 being at least 10. So if we purchased at least 10 apples, that would violate this constraint that we're supposed to have at most 9 apples. Okay? And then I could make another set B, which could be solutions with x2 being at least 7. So that would be at least 7 oranges. And then next I could create a third set, C, which would be solutions. Again, I'm referring to solutions from the ones that we've already counted here without the constraints. But this time solutions where the number of bananas is at least 6. So that would be x3 at least 6. And so what we're hoping to calculate now on this example is going to be the 21, choose 3, the total number of ways of buying 18 pieces of fruit with no constraints at all, minus the violations. And in this case, the violations could be any of these 3 types of violations, right? If any one of these limits on apples, oranges, or bananas is violated, then we have a scenario that we're not supposed to be counting, right? It's something we should be subtracting out. And so what we're saying here then actually is that the violations form this union, the union of A, B, and C. So we're going to now have to calculate what that number is. So let's see if we can do it. So I'll come back over here and write down my violations. And now is where we have the inclusion-exclusion principle for the size of this union. We're going to get the size of A plus the size of B plus the size of C, and then minus the size of A intersect B, and minus the size of A intersect C, and minus the size of B intersect C. And then finally, we come back and add the 3-way intersection of all 3 sets. So this is the inclusion-exclusion formula that we now want to calculate. So let's think about the size of A. And notice now all of the constraints are lower bounds on how many of the types of fruit that we would purchase, right? So these are now at least conditions. X1 is at least 10, X2 is at least 7, and so on. You may remember that when we have a situation like that on a stars and bars problem, we can imagine just running into the store, grabbing 10 apples, which we have no choice over. We must do this in order to satisfy a solution in set A. We take those 10 apples back outside of the store, and we go back in and we start over with an unconstrained problem now, where we would only have 8 more pieces of fruit to buy. So in other words, the size of A would just simply be 8 plus 3, choose 3. So instead of 18 plus 3, choose 3, we now only have 8 plus 3, choose 3. For the size of B, we would be subtracting out 7 of the fruits. So that would leave us with 11. And again, plus 3, choose 3. The 3s that are being chosen are the bars, which is always 3. So it's kind of nice to just keep that number on the bottom every time. And then the next one, where we take out 6 of our fruits from the 18, gives us 12 fruits, and we add 3, and then we choose 3. Okay, great. From there, I'm now going to subtract the two-way intersections. A intersected B would be solutions where x1 is at least 10 and x2 is at least 7. Well, that means you've already taken 17 pieces of fruit outside with you. So if you do that, then you only have one more piece of fruit to go back in and grab. So that would just give you 1 plus 3, choose 3. Next, we could look at A intersect C. And we can see that 10 plus 6 is 16. If we take that away from 18, it leaves us with 2. And so we'll be subtracting 2 plus 3, choose 3. And next we have B intersect C. That means we need to take away 13 pieces of fruit from the total. And that leaves us with 5. And we add 3 and then choose 3 once more. Finally, in the last scenario of the intersection of all 3, these would be solutions where we have at least 10 apples, at least 7 oranges, and at least 6 bananas. And as you can tell, that means you've already grabbed 23 pieces of fruit, which is more than the number of fruit that you started with in the first place. So actually, we don't really need to add anything back here. And if we tried to, we would be adding something in that was never counted in the first place, right? Because we only counted outcomes originally without constraints. We only counted the arrangements where we had 18 pieces of fruit chosen. Okay, so this now becomes our violations. And so you can imagine how we're going to get our answer to this problem. We're simply going to take the total, which was 21, choose 3, and apply the subtraction trick with this part subtracted. And so my final answer should be 21, choose 3, minus the quantity of 11, choose 3, plus 14, choose 3, plus 15, choose 3, minus 4, choose 3, minus 5, choose 3, and minus 8, choose 3, and then plus 0. And I'm using brackets around that violation piece, which you definitely need to do here for the algebra to be correct. So here we are, we have now subtracted the violations from the unconstrained total that we started with. So it's a nice combination of the subtraction trick together with inclusion-exclusion. All right, I paused my video for just a minute to kind of modify this problem just ever so slightly. I want to take a look at a slightly different question. I still want to go buy 18 pieces of fruit. I'm still looking at apples, oranges, bananas, and pears. And I want at most 9 apples, at most 6 oranges, at most 5 bananas. But now I also want at most 3 pears. The only real reason that I'm bringing this up is that we actually now have 4 constraints. And so we would end up creating 4 sets for each of the 4 individual sets, one for each of those constraints. And the violations would consist of a 4-way union. So just to be really clear, in case you haven't seen the 4-set version of the inclusion-exclusion principle, what we're going to have here is the same old 21, choose 3 again, which is the unconstrained arrangements of these 18 pieces of fruit that we want to buy, but now with a 4-way union of sets being subtracted. These would be the violations again, but now we have 4 types of violations. So just to be clear about how that will look when we write it out, it's going to obviously have a lot more terms. We're going to be subtracting the individual sets first. If we just simply remember with inclusion-exclusion that we kind of alternate plus minus with how many sets we are intersecting. So here we're going to start by subtracting the singleton sets individually. So then now that we come to the two-way intersections, we have to flip the signs back to plus again. So we'll have A intersect B added with A intersect C, added with A intersect D, added with B intersect C, added with B intersect D, and added with C intersect D. Every two-way choice of two of the four sets has to be considered individually here. So we have those 6 terms that we would be adding back in. And then we would be taking back out the three-way intersections. And now we actually have several of those. So I'll go ahead and write these down here as well. A intersect B intersect C, A intersect B intersect D, A intersect C intersect D, and B intersect C intersect D. Okay, and then finally, we would add back in the four-way intersections. So the 4-set version of the inclusion-exclusion principle is basically what's being subtracted right here on this bottom line of my board. And we could probably run through, although there's a lot of terms here, we could run through a calculation like this pretty quickly once we sort of have the idea, right? So we would take the 21, choose 3, and we would start subtracting all of these violations. The violations would be, x1 is at least 10, and then x2 is at least 7, x3 is at least 6, and x4 is at least 4. These are the types of violations that we would have, and we're literally just going to be subtracting these numbers from the top of our binomial coefficients. So like the first one would just be 11, choose 3. The second one, we would be subtracting 7 instead of 10 from 21. The next, so that would be 14, choose 3. The next one would be 15, choose 3. And on the next one, we would only be subtracting 4 from the 21. So those are the 4 individual sets this time. Okay, I'm going a little faster with this because it works the same way as the example we did earlier. The two-way intersections, we're going to be adding those. A intersect B, we have to subtract 17 from the 21 that's on top. Excuse me, then we have to add A intersect C, which means I have to subtract 16 from the 21. That leaves me 5, choose 3. A intersect D, we have to subtract 14 from the 21. That leaves me with 7, choose 3. The next one would be B intersect C. We have to subtract 13 from the 21. So that would be 8, choose 3. And then B intersect D, we would be subtracting 11 from the 21. That gives me 10, choose 3. And then C intersect D would be requiring us to subtract 10 from the 21 again. So that's 11, choose 3. Those are the the 6 two-way intersection terms. Then we flip back to minus again, and we start subtracting the three-way intersections. But we have to keep in mind that if the 3 numbers add up to more than 21, then those terms are really 0, because those kinds of violations are not possible given that we've only got 18 pieces of fruit that we're going to grab. So for example, A intersect B intersect C, these 3 constraints, the first 3 add up to 23, which is more than the 21 here, and so we would not have anything to do for that term. The next one is A intersect B intersect D, and that one is 10, 7, and 4. That's exactly 21. But again, if we take 21 away from 21, we're left with 0, choose 3. That's just 0, okay? So the number on top has to be at least 3 for this to be possible at all. So I'll subtract 0 there, all right? And then the next one would be A intersect C intersect D. And again, 10, 6, and 4 adds up to 20. If you take 20 away from 21, well, you get 1, choose 3, which is again just 0. And then the last one is 7, 6, and 4. And now that is 17. And if we take 17 away from 21, we do get 4. And so we could take 4, choose 3, right? So it is possible to have at least 7 bananas. So you could have 7 bananas, 6 oranges, and 4 pairs, and you even would have one more piece of fruit to still choose, which is why you actually would have 4 choices here, because that extra piece of fruit could be any one of the 4 types. Right? And then finally, the term that you're going to add back in would actually be 0 here. So there you go. That is another example of the inclusion-exclusion principle, this time using 4 sets instead of 3. I hope that this has been helpful to sort of see how we can sometimes use the subtraction trick together with inclusion-exclusion. Specifically, if the violations can be expressed as a union of several potential scenarios, then that union can be determined by calculating it through the inclusion-exclusion principle, and then that is what we would end up subtracting from the total. Of course, this can be generalized to more than 4 sets, any number of sets really, and the general inclusion-exclusion principle would then come into play for that. So I'll save that for another time, but for now, I hope that this has been a helpful illustration. Thank you for taking the time to watch this, and I'll see you guys again soon in another video. Bye for now.